share my screen. Okay, now we already, what we discussed just now is we changed the 2 times 2 matrix into 3 times 3 matrix. All right. And yeah, I introduced to you when we mention global matrix, what does it mean? Global nodal force matrix, it means that capital F and then the force that you see in the system, and then capital K, and also the displacement, right? Now, the step that we do is called superposition. The way that we transform the 2 times 2 matrices now is 2 times 2 to 3 times 3. The process is called superposition, which is what you see on the screen now. Superposition. The steps, I let you read through the slides. All right, the step is still same. So it means 2 times 2 to 3 times 2. We already do the steps already. All right, my slide just explain in more detail on mathematics order, how we do it. Okay, you read through. If anything you're not sure, you come and ask me. Okay, the concept is the same. Okay, how you move them around. Okay, the slide I show you is more step to go but it's more detail. Right. Okay. Now we look at boundary condition now. Okay, which is your tutorial. If you look at your tutorial, we look at your question number 5. Question number 5. So we need to look at a boundary condition. Why? Because we need to make our stiffness metric K to be non-singular. Okay, to be non-singular. So what is singular? What is non-singular matrix? You need to go and read Appendix A, or go back to your calculus or advanced mathematics. Go and read what is singular matrix or non-singular matrix. Okay. Now, what so far we cover is a spring system. So how we apply boundary condition to our spring system? In general, we have 2 types of boundary condition. One is called homogeneous, one is non-homogeneous. So in your tutorial, question number 6 is asks you how many types of boundary condition we have. So we only have 2. So homogeneous and non-homogeneous. What is their main difference? Their main difference is that homogeneous, it means that we don't have any movement. It means your displacement equal to 0. Then we have a homogeneous boundary condition. Okay, so if you look at the example just now, at point 1, you have no movement because it was mounted inside the wall. So at point 1, you don't have any movement. Then you have a homogeneous boundary condition. So it means that the point is not able to move if you have a homogeneous condition. Non-homogeneous is just opposite meaning. It means that we have a displacement. Okay, right. The wording that you see on the screen now is a textbook definition, or it's more appropriate when you write a report. So most of the time you use all these technical words. Okay, so you need to polish up your English when you write a report later on. Okay, so again, homogeneous, it means that your system not allowed to have any displacement or any movement. Non-homo, it means that you have a movement, you have a displacement. Okay, it means that your D component, F equal to KD, your D component have value there. Okay, if the question mentioned that you have a homogeneous boundary condition, it means that F equal to KD, the D component there's a 0 inside there. Okay, yeah, so we look at this one. Okay, so on the screen here, you look at one metric system. This consists of F equal to KD. I just move around the position, but it's still F equal to KD. Yeah? Any one of you are not sure what I'm talking about. What is F equal to KD? All right. So I just move around the matrix location. So this is F, this is K, this is D. All right. Now, all the boundary conditions such that the displacement are 0 at a certain node mean that we're trying to do what is homogeneous condition. It means that we look at a system, example that we have in your tutorial question number 3. Oh, yeah. So if you have a homogeneous, means that you look homogeneous, the word homogeneous, you try to link up with or tied up with the displacement. So you look at the system just now, because it's point number 1 is inside the wall. That's why we changed your U1 into 0. Okay, repeat, because you have we are looking at homogeneous boundary condition. The word homogeneous means no displacement, and in our system, there's one place that there's one location that do not move, which is your location number 1 or node number 1. U1 becomes 0. Okay. So if your system is 0, point number 1 is 0, you try to expand the equation. Okay, so you should be able to understand the one that I show you on the screen here. How you get the equation, again, I try to explain to you. So how you get this equation, you take the first row times this column, you get this equation. How you get this one? K1 times 0 plus 0 times U2 plus negative K1 times U3 equal to this one, the first one. And so on. You continue with row number 2 times first column, you get number 2, F2x. You continue the same concept, you'll get K1, negative K1 times 0, you get 0. Negative K2 times U2, K1 plus K2 times U3, and then you get F3x. Any questions so far? From the left to right and then to the bottom. We are now looking at homogeneous boundary condition, where in our example that you see in your tutorial, question number 3, why there's a 0 there? Because point number 1, node number 1 is on the wall. All right. Because your spring system is inside wall. This is point number 1 in the system just now. Okay. This is your system. So point number 1, node number 1 is inside the wall, because inside the wall cannot move. So you straight away go to your displacement component, you look at the point 1, you put 0. Then you transform back to the expanded equation to solve the question. Okay. Then after that, you have all this equation already. You already reduce the equation into a very simple equation. Okay. And here F1x you do not know. F2x, 3x you have they are applied force. All right. So because in your system, if you look at your tutorial question number 3 in your system just now, so you have 1 point, point number 3 and point number 2, and then you have two external force there, F2x, F3x, and then there's a point here. Because in your free body diagram, you have one force over here, F1x. Yeah. Now, why the direction to the left? Because I try to balance these two external force. I look at a bigger picture here. I look at global dimension, which is capital F. So if you have two capital F moving to the right, although I do not know what happened to the point 1, I know the direction that it must be balanced these two. So direction of my 1fx is to the left. And F1x is called reaction force. Reaction force, or R in your other module. Maybe other lecturer use FR, reaction. Okay, but for this module, we just use the more simpler form, F1x, to represent the location and direction. Okay, and F2x and 3x is called applied force or external force. So now we focus on the force, because F1x we don't know. So F2x and 3x normally is given, so we know the value of that. All right. So if you look at the equation, the matrix form that you have, right? The metric form that you have is 3 times 3 K matrix, and the displacement, you know that your point number 1 is mounted on the wall, becomes 0, and your force component, you have 3, 1, 2, 3. You do not know F1x, you do not know, but F2x normally is given. 3x normally is given because it's applied force, you know the force. So we're going to focus on these two components, F2x and F3x. So again, we're going to focus on these two forces. Again, you know that you can break your matrix into component, U1, U2, U3, U1, U2, U3. So since you're focusing on F2 and F3, you're focusing on this column. I'm going to highlight to you now. So we're going to focus on this section. Okay, I'm going to focus on this section. So what is the steps? So you just copy the matrix that you see in the system. You just copy the portion that highlighted on the screen now into a new space here. So your K matrix, what you see is K2 minus K2 minus K2, K1 plus K2 for the portion that you cut off. And then you look at displacement, U2 and U3, and then you focus on force 2x and 3x. Okay. Now to find the displacement, as you learn in your matrix in mathematics module, what you do is that you transpose, all right? You put the K -1, you pull your K from the left to right, you'll get -1. Okay, it's called transpose matrix times the force. So how you calculate -1 matrix, you go and read Appendix A if you cannot recall how you get transpose of how you calculate transpose of this one. Okay, this is 2 times 2 is more easy. There's one example in Appendix A that give you 3 times 3 matrix. 2 times 2 matrix input inverted or transpose is 2 times 2 is a bit easy, but when it become 3 times 3, you need to follow some steps. Okay. All right. So you will arrive at this stage. So from here to here is mathematics steps. So try to revisit. We don't have time to explain how you do the transpose of matrix into this answer. Okay, so I assume you already know how to do this one, because it's going to take us like 30 minutes to 1 hour to explain the steps, the mathematics step. And that one fall under mathematics module. I already assume you already know how to do this one. Okay, so after you do the transpose of your matrix, then you'll get this answer. And again, when you times your k into equation, you'll get what is u2, and you take this one times this one, you'll get u3. Take this one times this one, you'll get u2. This is how you solve a matrix. And also, this is also the reason why we use a metric system for FEM. Okay, so far we talked about homogeneous boundary condition. Okay, so after you substitute the external force or apply force that given in the question, and K normally you know, so by just applying your knowledge in metrics, you can find what is the displacement at point 2, what is displacement at point number 3. Okay. Again, go and revise how to do inverted or transpose matrix. How to go from these steps to this step. Go and revisit your mathematics skill. Okay. All right. So you just expand, just expand. So how you get this equation is just that you look at the equation just now, this one. So if you take this one times this one, you get F1. This one times this one, get F1x. So later in the slides, you see this one. K1 0 plus 0 negative K1 U3 F1x. Okay, so this one at the end, F1x, you only have minus K1 U3 equal to F1x. So you try to expand them in a reaction form. So you know, now we want to find what is F1x. Now, because in our system, let me draw just now. Spring 1, spring 2, point 1, 3, 2. You know that you have a 2 external force, right? So 2x, F, 3x. And you do not know what is the force at point 1, but you know the direction because it will try to balance the system. F2x and F3x is the external force that go to the right. So you know that the direction is to the left, but you do not know the magnitude. You don't know the F1. So how? What you do is that you call the equilibrium equation, all the force inside the system equal to 0. So what you'll get F1x will be equal to F2x plus F3x. Okay, then the negative is because of the direction. Right, the negative is because of the direction. Okay, so yeah, how you solve the simultaneous equation, you have to look back. So this is just a general guidelines, how you solve for the F1x. Right? So nothing complex there. Let's see if I miss out anything. Yep, it should be fine. The rest of equation, you can refer back to the slides that we just derived. Yeah. Let me see if I miss out anything. Okay. Now the next one, we look at non-homogeneous. Again, homogeneous means no movement. For non-homogeneous, what do we do? Okay. Now we look at non-homogeneous. This, if you're referring to a tutorial question, it will be under question number 8. The diagram is the same as what you see on the screen here. So I'm going to explain what happens if we have a non-homogeneous boundary condition. It means that we have a movement in all our system. So what does we have? If we have a non-homogeneous, it means our spring, all the point is moving. So a little bit different from a diagram that we see. If you look at the screen now point number 1 is moving with a delta. All right. So, and then the rest still the same. Only now because we want to look at non-homogeneous boundary condition example. So we just now in this section, we assume that point number 1 is moving now with the delta. Okay. So because point 1 is moving now under non-homogeneous discussion, non-homogeneous boundary condition discussion. So you just call back the general, the global matrix that you have, capital F again, global, and you have K1 and also so on. So this is the equation that we developed for a spring system that connected together. Okay. And because now we are looking at non-homogeneous boundary condition, point 1 is moving with delta. So just now, homogeneous case U1 we write as a 0, but now point 1 is moving with delta. So straightforward, U1, what you do is substitute U1 as a delta. Okay, so in a test, they will be given a value here. So in this case, we look at general equation here. All right. Now in the exam for this module, under my supervision, it will, every time you write a general equation, there will be a mark for that. So you want to secure marks, write general equation first before you solve your question. Okay. So for example, just a hint, if you write, before you start anything, you write F equal to KD, just like that. I'll give you 1 mark already, without solving any question. You look at the question, you see spring system, you write this equation, F equal to KD with the correct bracket form, curly for force, square for K, curly for D. You write this equation without any equation, without any further analysis, you get 1 mark already. So this is how you score for this module. And it's easy to get a B, grade B and above, if you follow the steps. Right, we're back to non-homogeneous. So non-homogeneous, again, it means that you have a displacement. So this example, we free up point number 1, where point number 1 moving with the delta. So we replace U1 with delta. Then we continue with the step that we learned just now for homogeneous boundary condition. So what you do, you just expand you take row 1 times column 1. Okay, row 1, column 1. Okay, so you just times, so K1 times, oh, sorry, I make a mistake here. You take this one and this one, you get this one. Okay, so how you get this equation? K1 times delta, 0 times U2, negatives K1 times U3, you get this one. And repeat the same for other two. So you get F2x, F3x. Okay. Now don't worry about the PowerPoint slide. Later on, you're going to get it. So in the lecture, try to understand what we are discussing. At least everything makes sense to you. Why we suddenly get these three equations and how you get these three equations. Okay. So again, you're just practicing your metric skill. So for non-homogeneous, because U1 is moving, so we substitute U1 with a known value, and then you expand, change the matrix into a formula form. Okay, you have these three equations. So at this stage, you should understand why you have these three equations. Why you have these three equations. Right. Now, again, F1x is our reaction force. And we rewrite these two equations in the matrix form. All right, equation 2 and 3 in matrix form. So without further explanation, you should know how to transform these two into this form. Okay, I did explain to you how do you get this one. So how do you get this one? This one is just actually you just move this term to this side. So you get K2 U2 plus K1 plus K2 U3 equal F3x plus K1 delta. All right. Why we want to write like that? Because our metric only 2 times 2, and we're focusing on displacement of U2 and U3. You cannot fit another one here, because if you have 3 times 3 times this one is 2 times 1, then your matrix going to break. You do not meet the matrix solution standard procedure. Okay, so from these two, you change to matrix form and it's solved. Again, how you solve? You move this matrix from left hand side to right hand side, you get matrix minus 1. And how you calculate matrix minus 1, go and see appendix A. Or go back to your calculus or advanced mathematics textbook, go and read how you get transpose or inverted inverse matrix, inverse matrix minus 1, inverse matrix. Okay, then you solve for F1x. You substitute the displacement in the first equation here. Okay, all right, because when you solve for because after you solve this equation here, after you solve this equation, you're going to get U2 and U3, by the way. So then you go back to first equation. This one you don't have value, but you know U3 value already. You know K1 value. So you know K1 value. You do not know the delta. You know delta. This one, the displacement will be given. So by all the value you have in equation, you're able to solve F1x. Okay. And just summarize boundary condition for stiffness matrix. The first one. This is your tutorial question number 9. There are 5 points that you need to understand, right, about K stiffness matrix. So K is square. K is square, as square means 2 times 2, 3 times 3. It means it relates to the same number of force in displacement. K is square. It also means that if you have 2 times 2, means that you only have, okay, let me recall the F equal to KD. So if your K is 2 times 2, it means that you only have 2 force here and 2 displacement here. Okay. So if your K is 3 times 3, it means that displacement component you have 3, means that you have 3 displacement, and also 3 forces here. Again, displacement, you can write in U, V, and W. If your movement is in X, means you use U. If your displacement in Y direction, you use V. If your displacement in Z direction, you use W. Okay, that's another reminder for displacement. So the first point, your K must be square depending on the displacement or force that you have. Okay, so if your force is 2, you know that you have a matrix 2 times 2. If your force is 3, means you have 3 times 3. Or you look at the displacement also. All right, you look at displacement, you have 2 or 3, depending on the system you have. Second one, the K can be symmetric. Symmetric means K minus K minus K. This is called symmetric. And then K singular. So when you have a singular matrix, the determinant, so if the word determinant still you're not clear, again, go back to appendix A, or go to your calculus textbook or advanced mathematics textbook. Determinant will be 0. Then when your determinant is 0 or your K is singular, then you cannot do inverse matrix anymore. Means you cannot do these steps. You cannot solve anything. All right. So you need to be careful. There are type of matrix that you have: square, symmetry, singular. And the main diagonal terms of K always positive. It means you see this one, positive, positive, positive. This is called main diagonal. Okay, positive, positive, positive. Always positive. Always positive. That's a reminder. Okay, this one you read yourself. What is, go to appendix A. What is semi-defined? What is semi-defined? It means that when you do your transpose, your K will become positive. Okay. Is there any question so far up to this slides? Any question?
Nope.
No. Okay, we have 2 more example. I think we continue these 2 example with this in your tutorial question number. We have 3 more example. Question 10, 11, and 12. We're going to discuss in our coming class this week. Yeah, after we solve this one, I think you're ready for your half of your test 1 already. Okay, right. recording.